Okay, so it's about time for us to get started. I think the first thing I'll do is just put up our schedule. Difficult to believe, but we're most of the way through the semester at this point. We're kind of 2/3 of the way through. Our final exam, you see the date on your self-service. I'm pretty sure it's the 8th of December, but don't hold me to it. I can't remember what time. If you get accommodations through the Blunden Center, I think they have to be booked 1 month ahead of time, 2 weeks for a midterm, a month for a final exam. So if you do receive accommodations through the Blunden Center, this is the time to get in touch with them. I'm pretty sure if you reach out to them kind of a few hours shy of the deadline, they're probably going to say no because they're completely overwhelmed. So if you get accommodations, this is the time to talk to them. And then test 2 is 2 weeks from today. I haven't really thought about your test 2 yet. I certainly don't have it written. The test 2 will primarily focus on the stuff we covered since the last test. And the cutoff will be like somewhere around November 10th. Once we get close to the cutoff, I'll let you know specifically. But it'll be, around the end of next week. So that's kind of coming. I think letting students bring in a sheet of notes to the first test, I think that worked reasonably well, so I'm going to go ahead and we'll say that that's good for the second test as well if you want to bring that sheet of notes. So I think that's all the housekeeping stuff I have to mention. Any questions before we get started today? Yeah.
You said primarily based on the stuff that we've covered since the first midterm.
Yeah.
Does that mean there could be questions based off of topics?
It's more in the sense that you can't forget everything we did in the first few weeks, because what we do after builds on what comes first. So, sometimes there's some overlap there, but kind of all the focus is on what we did since the first test. So last day we did more electric potential energy. We talked about equipotential lines, and we looked at equipotential lines with electric field lines. We got to the end of that chapter, and we're ready to start a new chapter today, chapter 24, which is about capacitors and dielectrics. So when we talked about capacitors in our electric field chapter, we said we had 2 plates, equal and opposite charge, and we used them as devices in circuits, and I brought in a circuit board and I showed a bunch of them. This is kind of interesting, and by the end of the chapter, we'll get around to talking about energy storage, and I think energy storage is really kind of neat. Capacitors store energy, but where and how? Like if you talk about spring energy, that's sort of easy to get because you can see the energy stored in the coils, but where is the energy stored in a capacitor, right? It's sort of a weird idea. So we're going to circle around to that as we get to the end of the chapter. We'll start with the physical device and how we use it in circuits. So we'll start with a reminder of our definition of a capacitor. 2 conducting plates, they each have an equal area A. They're separated by a distance D. When we draw our pictures, we tend to exaggerate this distance D just to make the pictures easy to draw. But these values of D are really very small compared to the size of the plates. So we'll write the word small there. We know the electric field between the capacitor plates is the charge density sigma divided by epsilon naught, and sigma is the charge over the area. Electric field is a vector, so it goes from the positive plate to the negative plate. There's our electric field. This space between the capacitor plates, sometimes it's just air, so sometimes there's nothing in there, and sometimes it's filled with a material that we call a dielectric. So that's what a capacitor looks like. We're going to start with it filled with air, and then we'll come around to talking about introducing the dielectric and what effect that has. We use capacitors in circuits, so when you build stuff, you almost always have capacitors in there. So we're going to be drawing circuit diagrams. And I guess most people are familiar with the idea of circuit diagrams from a high school physics class. So when we draw a capacitor in a circuit diagram, we draw plain lines to indicate ideal wires. And an ideal wire is just a wire that doesn't have any resistance or anything like that. It doesn't affect the circuit. And to represent a capacitor, we draw two small parallel lines. So this line is our capacitor. And then it's attached to another wire on the other side, and then those wires go off to the rest of the circuit. So when we see this in a diagram, this symbol tells us that it's a capacitor. When you order a set of capacitors, they'll come from the factory and they come uncharged. I can't say I've ever ordered capacitors. I reckon they come uncharged. If you want to get your capacitor charged up, what you have to do is connect it to a battery. So the first simple kind of circuit we're going to look at are capacitors connected to batteries. So we draw our capacitor. We label those with C for capacitor. We hook it up to a battery. When we draw a battery in a circuit diagram, we draw it with one long line, one short line. The long line represents the positive terminal. The short line represents the negative terminal. So your battery has two terminals. So this symbol is the battery. A battery can have two symbols in a diagram. Sometimes we call it delta V to indicate the potential of the battery. Sometimes instead of a V, we use an epsilon. Both of those things mean potential. So the potential we learned about in the last chapter, we're going to talk about that with regards to a battery in this chapter. Okay, we good to here? Okay, next we'll look at the details of charging up a capacitor. So I snagged this diagram from the textbook. I think it's a nice one for illustrating how we charge up a capacitor. So what we do is we take a battery, and this shows the inside of a battery. We hook it up to some wires, and our wires are also connected to a capacitor, which is our two conducting plates. So inside of a battery, I guess most people know that that's full of chemicals, which is why you don't want to have old batteries lying around, because sometimes it leaks and it can burn you. So inside the battery, there's some chemicals. There's a chemical reaction inside the batteries. That chemical reaction makes the charges inside the battery move around. What it does is it makes a positive ion, it makes a positive charge flow towards the positive terminal. So that's what the chemical reaction inside the battery does. It makes this positive charge flow forward. The positive charge leaves the positive terminal, travels along the wire. That's something you're probably familiar with as current, and we'll talk about current in the next chapter. So flowing charge is current. The positive charge hits the plate. Then we think about what happens. It has hit the plate, now it can't go anywhere. It's stuck on that plate, okay, because it can't leap into the air here because it's stuck on the plate. Now we have a positive charge here. This is a conducting plate down on the bottom. What's going to happen here is if there's a positive charge here, it's going to repel a positive charge from this plate because those charges are free to move. So a positive charge is going to come away from that plate. If a positive charge leaves, we're left with a negative net charge overall. And then the positive charge comes back around. This process repeats, dumping more and more positive charge on the top plate, repelling more and more positive charge from the bottom plate, until in the end, the capacitor is full. So the plates are holding as much charge as they can hold. And when that happens, the potential across the capacitor is equal to the potential across the battery. So when those potentials are equal, the charge won't flow anymore. So in our circuit diagram, we've got a battery here and a capacitor here. The charges move from the battery to the capacitor until the top plate has a full positive charge, the bottom plate has a full negative charge. After it's fully charged, the current stops flowing anymore. Everything is charged up. We take away the battery and we've got our charged capacitor. so let's get a few words to go with all of that. So charge flows from the battery to the capacitor until delta V, the potential difference across the battery, equals the potential difference across the capacitor. Once those two things are at the same potential, the charge won't flow anymore. And at this point, the capacitor carries its maximum charge. Okay, any questions about the process? Typically, this is a very fast process. You know, you wouldn't hook this up and go make a cup of tea. You hook it up and it's finished by the time you can blink. Okay, so it's very fast. Okay, so next step is let's talk about this capacitor and how we can characterize it. So when we talk about batteries, we say that they have a certain voltage or a certain potential, like you might buy some 1.5 volt batteries. When we talk about capacitors, we say they have a capacitance. Okay, so capacitors are characterized by capacitance. Capacitance has a symbol of a capital letter C. The units of capacitance are farads, which has a symbol of a capital F. A farad is very big, so when we talk about capacitors, typically we're going to talk about microfarads, so 10 to the minus 6 farads. Nanofarads, 10 to the minus 9. Picofarads, 10 to the minus 12. And once in a while, femtofarads, 10 to the minus 15. Okay, so a farad is really big. Typically, we're going to have very small values. So, how do we talk about C? So let's talk about our capacitor. There's the picture of something we have. There's the picture of how it gets charged up. Let's go back to what we talked about in our electric fields chapter. When we have a positive and negative plate, we know that the electric field is the charge density sigma divided by epsilon naught, and it points from positive towards negative. So our plates each carry a charge Q. This one is positive Q, this one is negative Q. They each have area A. That sigma is Q over A. So one has a positive charge density and one is a negative. The two plates are separated by our distance d. Our electric field points from the positive to the negative. We remember that electric field points from a high potential to a low potential. So we'll put a reminder here that there is a potential difference between the plates. And so this one is at high potential, this one is at low potential. So there is definitely a potential difference between the plates. So let's try and get to an expression for our capacitance C by thinking about the things we already know, the electric field and the potential. So our electric field is sigma over epsilon naught. We'll deal with magnitudes for right now. So the size of the field is the size of the density divided by epsilon naught. Charge density sigma is charge divided by area. So that's Q over A times epsilon naught. So this is one expression for the electric field between the capacitor plates. We can also write down the relationship between the electric field and the potential. We know that the size of the potential difference is the size of the field times the plate separation d. Okay, so good to hear. Okay, and we're still talking about magnitudes. So let's put these two things together. Delta V is E times D, but this is E, so let's just do that substitution. So the potential difference between the plates is Q over A times epsilon naught times the distance between the plates. Q is the charge on either plate. I'm going to rearrange this equation so I get Q on the left, everything else on the right. So my charge Q is equal to A times epsilon naught divided by D times delta V. So this equation shows us that the amount of charge on the plates is proportional to the potential difference across the two plates. Our capacitance C is that constant of proportionality. Okay, so they're proportional, they're linear. So we define our capacitance C equals A times epsilon naught divided by D capacitance. What's interesting about this is that the capacitance only depends on the physical properties of the capacitor. It depends on the area of the plates, it depends on the distance between them, and this epsilon naught is the permeability, permittivity of free space. It's how the electric field acts in a vacuum. So it also depends on what's between the plates. So this is strictly a property of the physical characteristics of the capacitor itself. If we think a tiny bit more about our units, so a farad, capacitance is charge divided by potential difference. That's going to be a coulomb divided by a volt. And a volt is a joule per coulomb, so that would be coulomb squared over joules. So to break it down into our SI units. And this relationship between the capacitance units, it has farads in it, is related to joules. That's an indicator that capacitors are related to energy storage, right? So we see energy here in our units, so capacitors are important for energy. Okay, questions to here? Okay, so one application of this that might be interesting to the musical people in the class. Got any musicians? Yeah, there's usually some, even if people don't really want to admit it. Apparently science brains and music brains go really well together. Like often people who are good at science are also really good at music. I am not one of those people. I don't have any music talent whatsoever, but I admire those who do. So singers often use what's called a condenser microphone. Musicians heard of that one before? Condenser mic. This is kind of neat. So inside the microphone, there is a capacitor. And you know how you store sound on your phone or your computer or whatever, it stores it? If it stores it, it has to store it as an electric signal. That's the only way it can interpret information. So what happens here is inside the mic, there's a capacitor. One plate is flexible. Okay, so one plate is fixed and one can move. As you sing, your voice hits the microphone and it makes that flexible plate move in and out. The capacitance depends on the distance between the plates. So we saw that in our previous equation. Depends on the distance between the plates. So if you change the distance, you change the capacitance. This thing is hooked up to a constant power supply. So if we keep delta V constant and we change the capacitance, it means we change the charge. So as you sing and your voice makes that plate flow in and out, the changing capacitance makes the charge flow. Flowing charge is a current, and the circuitry detects that current and it's able to store the sound. Okay, so that's sort of neat. And we'll see some other places where capacitors work like that in circuits. Okay, questions? So let's get a conceptual example. A capacitor has a vacuum in the space between the conductors, so just like the capacitors we've just been drawing. if we double the amount of charge, what happens to the capacitance C? So I'll give you a minute to think about it and pick your answer, and then we'll see what people like. Okay, that's been about a minute. Now it's time to commit to your answer. So if you got a pen and paper in front of you, you should write down your answer or circle your answer. If you're not taking notes, then make a definitive statement in your head. I think the answer is this. You gotta be able to check your answer afterwards. So does anybody want to share what they think their answer is?
Possibly 3.
Okay, so we got an uncertain 3. Anybody feeling the same way? 3, but not going to fight to the death over it?
Would it be 4 because the area?
Yes.
Okay, so we got a 4 because the answer depends on the size and the shape. Anybody else like 4? Oh, we got some other answers for 4. Okay, so for our questionable number 3, anybody have a reason for that one? Okay, how about other answers? Okay, so we're down to 3 and 4. So let's go with the most straightforward answer first. Capacitance equals A times epsilon naught over D. So to the comment that capacitance depends on the area and the space between the plates, I agree with that statement, it's absolutely true, but we're not changing the area or D. Okay. Does this equation depend on the charge? Not at all. Okay, so if we double the charge, nothing happens here. So it remains the same. Okay, but what about, since Q is the capacitance times delta V, what about the fact that C is Q over delta V? Shouldn't C change if we double the charge?
The same amount of charge will leave, it would be the same proportion
Okay, so the comment is it would be the same proportion.
of charge, leaving one plate to the next. It would just be 2Q instead of 2Q.
Right, so our original capacitor has Q over delta V. Our new capacitor has C primed, Q primed over the new potential. This new charge is 2 times the original charge. Okay, good things to think about, right? So why don't we ask, if we double the charge, does anything happen to the potential? That's a good question, right? So let's look at what happens to the potential if we double the charge. So let's think about delta V. So our potential difference is the electric field times the distance between the plates. So we're going to say our new potential is our new field times our distance. Distance doesn't change. Electric field is charge density divided by epsilon naught. So our new charge density divided by epsilon naught times C. charge density is charge divided by area. Our new charge, remember, was double our old charge. This was our original electric potential. Okay, so if we double the charge on the plate, we actually double the field and we double the potential. So in this expression, we get 2Q over twice delta V equals Q over delta V equals C. Okay, so the capacitance changes because the potential changes with the charge. Okay, I was afraid that might be too easy of a question, so I'm glad it was worth thinking about. So let's get into a numerical kind of question. Oh, and those of you who are right, get to put a star on your paper. Get the right answer. Okay, we have three capacitors. Let's find the capacitance in each of the three capacitors. So this will take us through some different ways to calculate the capacitance. So number one, a capacitor that has 120 picofarad, my goodness, picocoulombs on each plate with a potential difference of 10 volts. So for number one, we know the charge and we know the potential. So our capacitance is our charge divided by our potential difference. 120 times 10 to the minus 12 coulombs divided by 10 volts equals 12 times 10 to the minus 12 farads equals 12 picofarads. Okay, so capacitance is the ratio of charge to potential difference. Number two, a capacitor has 50 millimeter square plates separated by 1 millimeter. So 50 millimeter square plates means your capacitor has square plates. The length of each side is 50 millimeters. So capacitance is area times epsilon naught divided by D. Area is going to be the length times the width. So 50 times 10 to the minus 3 meters squared times epsilon naught divided by the distance between the plate, 1 millimeter, gives us a capacitance of 2.21 times 10 to the minus 11 farads. If you like that picofarad business, 22.1 picofarads. Okay, so those are the two basic ways we have to calculate a capacitance. If we wanted to make it just a little trickier, a capacitor has a potential difference of 150 volts, that's delta V. We have an electric field of 500,000 newtons per coulomb between circular plates with a radius of 2.5 centimeters. So we don't have enough information to use either this equation or this equation. So let's see what we can do here. So let's start with the idea that our capacitance C is the charge on either plate divided by the potential difference between the plates. We know there's a relationship between electric field and charge density, and we know the charge density depends on the charge. So thinking about the electric field feels like it could lead us to what the charge is. So let's go there. So our electric field is charge density divided by epsilon naught. Charge density is charge over area. So there's our electric field. Our plates are circular, so the area is pi r squared. In this expression now, we know E, we know R, so we can solve for our Q. So Q is equal to pi r squared epsilon naught times our electric field. So let's pop that in for Q, and then we'll be able to find our capacitance C. So we've got pi times 0.0250 meters. That's squared epsilon naught 8.85 times 10 to the minus 12. Times E 500,000 newtons per coulomb. Divided by delta V, which was 150 volts, to give us a capacitance C equal to 5.79 times 10 to the minus 11 farads, or in terms of picofarads, 57.9. Okay, any questions there? So that takes us through more or less how a single capacitor works. The next thing we're going to talk about is when we have circuits. In our circuits, we have lots and lots of capacitors. You rarely just have a single capacitor. Normally you have a whole bunch of them, which means they have to be connected together. So we're going to look at how do we connect capacitors and how do we deal with those in circuits. If you did high school physics, this is going to be not dissimilar to when you connected resistors. So we're going to do the same sorts of things here. So the first way we'll talk about our connection is going to be the series connection. This is the easiest one to analyze. When we talk about a series connection, we're talking about things connected all in a row. So we hook a wire up to our battery. The wire comes out of the battery, plugs into the first capacitor. A wire comes out of that capacitor into the next one, out of that one, into the next one, out of that one, back into the battery. So they're all in a row. So they're joined end to end, all in a row. So our charging process here, what's going to happen in this circuit is that through the chemical reaction inside the battery, a positive charge is going to leave. It's going to come up around, come through here. We're going to hit the top of this plate. It's going to repel a charge from this plate, leaving that one positive. That charge that leaves this plate is going to hit this one. Then that's going to repel a charge from here, which is going to hit this one, which will repel a charge from here, come around, and come around. That charging will happen in that fashion, and what's going to happen is for every charge that hits here, will repel here and hit here, repel here and hit here, and so on. They all have to have the same charge, okay? Because every single charge that goes out through here essentially hits every one of those capacitors. So in our diagram, we can say that charge 1, or charge on the first capacitor, we can call that Q. Charge on the second capacitor, we can call that Q. Charge on the third capacitor, we can call that Q. So all three capacitors have to carry the same charge. So every capacitor connected in series carries the same charge. So that tells us about our charge. What about our potential difference? So every capacitor has a charge. That means there has to be a potential difference across all of those plates. The potential difference is supplied by the battery. There's a finite potential supplied, so it has to get divided over the three capacitors. Okay, so the potential difference will split over the three capacitors. So our first capacitor will have a potential delta V1. Second will have a potential delta V2, and the third will have a potential delta V3. So the potential splits over all three capacitors. if we're saying it's split over all the capacitors, a way to write that down in an equation is that delta V, the potential supplied by the battery, is the potential across 1 plus the potential across 2 plus the potential across 3. Okay, so it splits over the 3 of them. If we remember our relationship between charge, capacitance, and potential, we know that Q is C times delta V. Or C times delta V. So delta V is Q over C. So V1 is charge 1Q divided by C1. Delta V2 is charge 2, which is also Q, divided by C2. Delta V3 is charge 3 divided by C3. Okay, so there's an expression for the total potential supplied by the battery. Okay, what next? So often we can, and we do for analyzing circuits, we could take out these 3 capacitors, we could pop those 3 out, we could put in a new capacitance, we call that C equivalence, and this new capacitance would carry the same charge Q when connected to the same battery with potential delta V. So that's what we call an equivalent circuit. We take out what we have here, we put in a single capacitor, and we get the same charge for the same potential. So we create what's called an equivalent circuit. So we go from here to here. And our equivalent circuit is we replace C1, C2, and C3 with an equivalent capacitance called CEQ. And that has charge Q and potential delta V. So that means our equivalent capacitance CEQ would be the charge divided by the potential delta V. You good to there? So if CEQ is Q over delta V, it means delta V is Q over C equivalent. That can come in down here. So delta V is Q over C equivalent. If we look at our equation, we've got Q in the numerator in all terms, so we can divide both sides by Q, and we are left with the result. One over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. And then if we had more capacitors, we would just keep adding them. This is how we find equivalent capacitance for capacitors connected in series. If you're thinking back to your high school physics, you might recognize this as being a similar form to your resistors connected in parallel. Be careful you don't get those tangled up in your head when you're doing your calculations. Capacitors and resistors are different. So make sure you know which form of equation goes with which. Okay, we're good to here? Okay, so another kind of interesting application of capacitors connected in series. This is actually how touch screens work. So like everybody's phone, I guess, pretty much everybody has a touch screen these days. A lot of laptops and the smartwatches. So inside your phone, underneath the screen, there's some layers of transparent material. They're conducting and there's a potential difference across them. And they're crisscrossed. So there's these layers that are crisscrossed like this. Those crisscrossed layers make a capacitor. And then your phone screen and your finger make another capacitor. So when you touch somewhere on your phone, you now have two capacitors in series right above that point. Your phone has circuitry that can detect the fact that the overall capacitance has changed, and that's how it knows where you touched it. So I think that's kind of cool. Okay, so let's go on and do an example. So I put a really easy homework example here. What if your three capacitors are 1 picofarad? We'll do something just marginally more difficult. So what if we have three capacitors connected in series to a 30-volt battery? Let's find the charge on each capacitor and the potential across each capacitor. So right off the bat, we know the charge on every capacitor is going to be the same. So let's just make a note of that. Charge is going to be the same because capacitors in series all carry the same charge. And we know that this 30-volt potential is going to be split over the three capacitors. Okay, so now we have an idea of what we expect for our answer. So let's do an equivalent circuit first, because we know the individual capacitors, we know the potential. If we can find the equivalent capacitance, that'll let us find the charge. So let's start there with our equivalent circuit. So we'll draw our equivalent circuit. We've got our 30-volt battery connected to an equivalent resistance. And to calculate our equivalent equivalent capacitance. To calculate our equivalent capacitance, we do 1 over C1 plus 1 over C2 plus 1 over C3 equals 1 over 12 picofarads plus 1 over 22.1 picofarads plus 1 over 57.9 picofarads. We'll do that through the calculator, so if you add up those three digits, we get 1 over C equivalent is 0.146 picofarads to the minus 1. Take the reciprocal, and C equivalent equals 6.86 picofarads, where pico means times 10 to the minus 12. Something that maybe pops out here is that when you connect them in series, the equivalent capacitance gets smaller. So when you connect them, you get a lower capacitance. So let's use this idea now. Let's find the charge on the equivalent capacitor, which will be the same as on those three. So C equivalent is equal to the charge Q divided by the potential difference. So Q is C equivalent times delta V. 6.86 times 10 to the minus 12 farads times 30 volts gives us a charge of 206 times 10 to the minus 12 coulombs, or 206 picocoulombs, whichever you prefer. This is going to be our charge on 1, on 2, and on 3, because series have the same charge. To find our potential difference, now we know each of the capacitances, we know the charge on each of them, we can find each of our potentials. So the potential across the plates of the first capacitor is going to be the charge on those plates divided by C1, 206 times 10 to the minus 12 coulombs, divided by 12 times 10 to the minus 12 farads, gives us 17.1 volts. The potential difference across the second capacitor is 206 times 10 to the minus 12 coulombs, divided by 22.1 times 10 to the minus 12 farads. That potential difference is 9.3 volts. And across the third, we do Q over C3. So 206 times 10 to the minus 12 coulombs divided by 57.9 times 10 to the minus 12 farads. Potential difference across that third capacitor is 3.6 volts. And if you looked at your potentials, you would see that together they all add up to be 30 volts, right, because it all got split over the three capacitors. Okay, any questions there? We still have like 4 minutes left to go, but this to me feels like a good place to quit because we're finished our series circuits and next we'll go on to parallel. Like 4 minutes is not a lot of time. Yep, you have a question?
The problem session this coming week.
Yep.
What topics is that going to cover?
I just made that up this morning. I've got it about electric potential energy, the equipotential lines and electric field lines, and some of the simple capacitor stuff. Okay, so we're good there and we'll be back on Monday.